Now let us see the applications of law of conservation of energies, where we can apply law of conservation of energy. So we will take few examples. So before some few examples, let us first see how to express the kinetic energy of a system, of a very complicated system like a distributed mass system. So let us take an example 1. So this is example, first example. So what I do, I have a spring. So this is a spring and its length, initial length is something, and it is elongated, it is stretched with a constant velocity v. Initially it has some length. Now I have to calculate the kinetic energy of this spring. This spring has a mass. So kinetic energy of a massive spring, This is what we want to calculate. Now we have a spring here whose mass is m, and I want to know what is the kinetic energy when it is one of the ends is pulled. So you see, I am pulling one of its end. So when I pull it, there will be a uniform elongation like this. So let us consider a small portion of it, this portion, small portion, and let at that instant the total length is L. So consider a small portion of spring of length dx at a distance x from the fixed end. So the spring has one end fixed and another is pulled with, the free end is pulled with velocity v. So we can say that let that x is equal to eta times L. So L is the instantaneous length, and in order to know where we are, so let us consider the element at a position x, which is eta times L. So this is point 1. If I differentiate x, I will get eta times dl by dt. Now again back substitute eta. Eta means x by L. We have dl by dt, that is x v by L. So I got the velocity of this point as something x v by L. So you see, when x is equal to L, this is velocity. When x is equal to 0, the velocity is 0. When x is L by 2, velocity is vcm, that is half of v. That means all the particles have a different velocity at a point. So let us calculate dk, the kinetic energy of that small element. Dk is half dm into v square. So dk becomes half, dm means mass, by L into dx. This is dm, and v square means x square, v square by L square. So on simplification it becomes m v square x square dx by 2L cube. Now I integrate it. So on integration I will get k is equal to mv square by 2L cube integration of x square dx from 0 to L. That is mv square by 2L cube, this L square by this, sorry, L cube by 3. So that is L cube gets cancelled. So we have m square by 6. So what I got, the result, that if it is a mass, if we have a point mass, then its kinetic energy is half mv square. But this spring is a massive spring, is a distributed mass, so its kinetic energy becomes mv square by 6. this will be very helpful when we study that if a block is kept here and then it is under oscillation, then what is the time period of oscillation? At that time, this spring will be able to store energy in the kinetic energy form as well as potential energy form. So the kinetic energy of that spring will become mv square by 6. So now let us take another example. Now we have a spring here. This is fixed and we have a spring here. So you can see this spring. So this is the natural position of the spring, and what we did, we have compressed it. So when I compress it by applying an external force, slowly I have applied, and by applying an external force P, I have compressed it to a position x naught. So this position is x naught. So a spring is compressed by x naught by applying a constant force P. Now we have to calculate that if this spring is suddenly the force P is reversed. So suddenly the force P, the direction of the force P is reversed. So here the direction of P is reversed. So from pressing, now it is elongating. So what is the maximum value of elongation? So a spring, this is massless spring. A spring is compressed by x naught on the application of certain force. On the application of certain force. The force is then reversed. And now calculate the maximum elongation. So this is what we want to do. We have to calculate the maximum elongation. So you see, suddenly the force is reversed, and let us do it. Please write down this. So now first you see this P is how much? If I assume the spring constant is K, then P is equal to Kx naught. This is one thing. Now here there are two positions. This position is A and this position is B. So now let us apply law of conservation of energy, at A and B. So throughout the motion there is an external force doing work. So we have initial kinetic energy at A plus potential energy at A. Since there is work done from A to B, so that will be work W is equal to KB plus UB. Now since here it is at rest, and it is at rest because it at maximum elongation velocity of B is 0. So this quantity is 0 and this is also 0. So this is 0, and potential energy at A, you can see it is half K x naught square. Work done, you see this is x naught and suppose this is x. So work done is P x naught plus x is the external work done by the external source in this system. And then KB is 0, this KB is 0 this term, plus UV. Now here the elastic potential energy, the spring has half K this x square. So this is the energy stored here. So now you see here this we have to calculate x. So this is kx naught square by 2 plus px naught. This px I will bring there so that all x will be at a one place. So this is k by 2 x square minus px. We don't know p, so we can put p is equal to kx naught. So this is kx naught square by 2. This p is kx naught. So kx naught square, that is kx square by 2 minus p is kx naught. So kx naught. So here you get the value of 3kx naught square by 2 is equal to kx square by 2 minus kx naught. K cancel. Multiply by 2, I will get x square minus 2x naught. Then again I will bring this 3x naught square is equal to 0. So now you can see I can put it into 3x naught plus x naught minus 3x naught square equal to 0. I can take common 3x naught, then plus 1 x minus 3x naught equal to 0. So x plus 1 into x minus 3x naught equal to 0. So x is equal to 3x naught we got. That means this maximum x is 3 times x naught. So here I have used the general work energy theorem or the general law of conservation of energy, that if there is initial energy in the system, this is the initial energy in the system and this is the final energy in the system. If there is no work done, then this is equal to this. But if there is a work done, so P is doing extra work from A to B, that extra work has to be taken care of, and so we get x is equal to x naught. Now let us take one more example. This is example number 3, where I have a spring. Suppose I have a spring here and this spring is connected to a mass m. This spring is connected to a mass m. Now what I do, I started pulling by applying a increasing force. So initially my force is very small, I applied it, then I am applying more force, and then slowly I am applying. So when I apply F naught force, the spring breaks. So slowly. So what is given? So when a mass hanging with a spring is pulled slowly by an increasing force. So doing this is actually called, in technical language, in physics we call this quasi-statically. That is slowly. If I move it slowly so that each time it is in equilibrium, then the spring breaks. When force is F naught. So when I reach my force up to F naught value, then the spring breaks. So this is the breakdown position. Find the minimum constant force that should be applied to the hanging spring mass system so that it breaks. So in order to break, What is the minimum constant force that has to be applied? This is our point. Now, you see, I have to apply this slowly. So let us see what happens. So when I apply it slowly, it breaks after reaching this. So you see, this is the natural length of the spring. So this is the natural length of the spring. So when there is no force, this is x naught, that is equal to mg by k. So you see, if there is no force, it will still have certain elongation. Now when this force becomes F naught, then you see, so when the spring breaks by applying a increasing force F naught, then in that case the total elongation is kx is equal to mg plus F naught, implies x is equal to mg plus F naught by k. That means this elongation is measured from here. So the moment the spring total elongation becomes x, then it breaks. That means we need not require this elongation. If the spring is here, it will not break, but the moment it reaches here, it will break. So what happens when the situation is that the spring is already here with this mass? So when I apply F naught, not F naught, some different F, then my F should be less than this. Why? Because somewhere my equilibrium position, that is that this is spring force and F should be here. So what should happen? So when I am continuously moving it, not slowly, then the moment it reaches here, the total force is 0, but it overshoots its position, and so it comes here and then it will be moving like this. That means I have to apply certain force if not less than this, because when you apply slowly, this is the equilibrium position, this is the equilibrium position. When you applied F naught slowly, this is the equilibrium position where it is going to break. But when you apply this F continuously, the equilibrium position should be here, because it goes more than the equilibrium position. So this force should be less. So now it can reach here. That means the moment by applying a force F naught, it reaches here, its kinetic energy must balance, must be 0. So this is position B and this is position A. So now applying work energy theorem at A and B. So what is the total energy in the system plus work done? This. So, or law of conservation of energy, anything you can say, A and B. So at A, suppose my datum is itself A. That means I assume that the gravitational potential energy at A is 0. So already there is some spring force. That spring force is half K, that mg by K whole square. This is already the spring force and no other force is there. And then in that spring force, I have done some P force. I have applied and moved to this position. This position is x, this total x minus x naught. This is x minus x naught. So I have done work only from here to here, that is x minus x naught. That is, and there was no initial kinetic energy and there is no final kinetic energy. But there is a loss in potential energy, that is minus mg. This is loss in potential energy minus mg. This distance is x minus x naught. And then there is a potential energy half kx square. So I have to calculate the value of P, and I know the value of x also and x naught also. So what I do, this is half k mg by k whole square plus x minus x naught. So this is x naught is mg by k. So x minus mg by k is simply f naught by k. So this is p f naught by k is equal to minus mg. This is x minus f naught is f naught by k plus kx square by 2. So now you see here we want p, and this is k by 2 m square g square by k again, because 1k cancel. So 1 by 2 m square g square. So this is p times f naught plus mg by k is equal to this kx, k by 2 x square. Now x square is mg plus f naught by k square. So this is square, and so this is k square. So let us write it 1 and only k. So again you see p f naught plus mg by k is equal to half. This is, we can subtract this here. So it will be 2 by k. Here we have m square g square plus f square plus 2 mg f naught. This is, and here minus m square g square goes on, minus m square g square. So here you see m square g square cancels out and k cancels out. So we have here p into f naught plus mg is equal to, here f naught if I take common. Now you see this k cancels. So here we have 2. So what we do then implies this p is equal to p into, this is f naught plus mg, f naught plus mg, that is equal to, this is 2 f naught. F naught I can take common. So I can take f naught common. I will get f naught here and here 2 mg. 2 mg by f by 2. So this p will be equal to, I have to divide this. So will be f naught times f naught plus 2 mg by 2 into this f naught plus mg. So this p will be equal to this. This is the amount of p required to, so that this p you can see is less than f naught value. This will be less than f naught value. So thus when we have to move this down with a constant force and one with slowly and one with constant force, that means the equilibrium position will be different. So you can see how we have applied law of conservation of energy at A and B. Now let us take another example. So this time I have a rod here. This rod is fixed. This is the vertical rod fixed, and we have a ring of mass small m connected with an inextensible thread which passes over a pulley, and to the other end is a hanging mass m. This m is greater than m. So this is my ring, and this distance from here to here is given L. Now at this horizontal position I release this ring. So the question is how much distance it will fall. So when the ring is released from the horizontal position, then how much maximum vertical distance it falls. This is what we want to do. Now let us discuss the motion. So when I release it, you see here we have a tension T and here is a reaction which balances tension. So there is no force to balance mg. So even if this is small mass and this is heavy mass, it has to come down. So it will come down to this position. So if I slowly release it, what will happen? At this position, the T has a vertical component that can balance. But if I release it slowly, then this is the equilibrium position. But if I release it, it will come to this position, acquire velocity, and it will overshoot its position. And so it will come to this position. This is the maximum distance. This is the maximum distance. It falls down. This is h. Maximum distance it falls, that we have to calculate. Maximum distance h. Now you see here what type of motion this ring will exhibit. So here the component of T in this direction balances weight. So here the force is 0, but as the ring slides down, here it is under acceleration. And when it is here, then it is under acceleration in this direction. So this is the mean position. So this is an oscillatory motion. So the ring will oscillate like this. So we want to know presently that how much maximum distance it can come down. Now what we do, we will apply that since here the velocity is 0. So how much potential it is lost, that is the gain in the potential of this mass. So this mass moves here at a height x. So let us see what is x. So let us first relate x, find x. So how can I find x? The total length of the string remains constant, since the length of the string remains constant. So how much distance is fall? So this is the new length and this is the old length in this side. So root over, this is L square plus H square minus original length L is the total distance x. So bring this L this side and square it. So L square plus H square becomes x square plus L square minus 2xl. So here you see, so let us just write this only. So no need of doing this, or L square cancels. So let us just write this x equal to this much only. So let this be x only. So now loss in potential energy of ring is equal to gain in potential energy of M. Loss in potential energy is ring mgh is equal to gain in is mgx. So gg cancel, mh is equal to mx. So x value will put here. So mh is equal to m, x value is root over L square plus H square minus L. Now we have to calculate this value of H. So we will put mh plus ml whole square is equal to m square L square plus H square. So we have, now let us square this, m square H square, this is capital ML plus m square L square plus 2mh ml is equal to m square L square plus m square H square. So this term cancels out and we will bring this h here, implies m square minus m square H square is equal to 2, this is minus here, so this is 2mhl. So 1h cancel, so h becomes 2mm by m square minus m square. So this is the value of h, the maximum distance it falls down. So now take another example. We have two identical masses and we have a spring here. So the spring is compressed from its natural position and tied with a string. You can see this string in between them. So we have to find how much I should compress the spring from its natural position and tie it, so that when I burn this thread, then this will jump off and it will just leave the contact. So find the compression in the spring, so that when the string is burnt, then the lower block just leaves the contact. That means when it will jump off, it will just leave it contact. So for which how much it should be compressed from the natural position. This is the problem. Now suppose the natural length of this spring is up to here. So this is the natural length. So that means this spring is compressed initially by x naught. That has to be determined. What is this x naught? So that when it goes on, so you see here, this is the new situation. So the spring is elongated, and because it was compressed, so the first mass will move up and it goes up to this position. So it goes up to this position x. So this is x. Now when this is the natural position of the spring, so when it goes x, that means this time it is elongated by x, and the lower block will lose contact when mg is equal to kx implies x is equal to mg by k. So when x, the elongation becomes mg by k, it loses contact. So now I have two positions. This is position A and this is position B. So applying law of conservation of energy at A and B. So you see at A, suppose I assume that the datum is this much, this natural position is the datum. So at A, the kinetic energy is 0, Ka plus Ua is equal to Kb plus Ub. So kinetic energy at U 0, Ka at A, the system has two potential energy. Elastic potential energy of spring is half kx naught square, and gravitational potential energy is minus mg x naught. This is x naught. At UB, this kinetic energy is 0, then potential energy. Elastic potential energy is half kx square and potential energy is half mgx. So we have to calculate the value of x naught for which that will lose contact. So x value is mg by k, we know. So we have to calculate x naught. So kx naught square by 2 minus mgx naught is equal to, next here, kx square by 2, kx square. So we know this kx square value. So x is already known. X is equal to mg by k. So k by 2, x means mg by k, m square g square by k square plus mg, x means mg by k. So we have now k x naught square by 2 minus mg x naught is 1k, 1k cancel, m square g square by 2k, m square g square by k. So 1 plus 1 by 2, 3 by 2, m square g square by k. So I multiply both sides by 2k. So we will have k square x naught square minus, this is again 2k mg x naught minus 3m square g square. So this is a quadratic. Again you can see this is a quadratic, and so we can express this k naught x naught square and this minus here, so equal to 0. So I can write it as 3k mg x naught plus k mg x naught minus 3m square g square equal to 0. So I can take here k x naught common. So I will get k x naught minus 3mg plus, here I will take mg common. So k x naught minus 3mg equal to 0. So k x naught plus mg is equal to 3k x naught minus 3mg 0, implies x naught is equal to 3mg by k. So thus we got that initial compression in the spring must be equal to 3mg by k, so that this lower block loses the contact with the ground.